everyone. I'm Dave Rowland. I'm the Director of Software at Traction. We make a digital audio recording workstation. We make virtual software instruments, and on the Prism brand, we have hardware interface boxes.
I'm Fabian Renn Giles. I've been working in the audio industry for over 10 years, and I am a consultant for real-time audio and real-time systems.
We've got quite a lot of material to get through today, so it's probably best to keep questions at the end to make sure we get through everything, but make a note of the slide numbers if you want us to jump back. Can I get a quick show of hands? Who does real-time programming in here, even if it's for a hobby project? Okay, yeah, quite a lot of people, cool. So a quick bit of prior art here. Has anyone seen Timur Dumla's talk, C++ in the audio industry from CPCon a few years ago? Good number. That's a really good resource to go and look at if you want to get some introduction to the audio industry. And also this article by Ross Bensina gives a good overview of some of the background of things we're going to talk about today. So first of all, we kind of need a definition for those who don't do real-time about what does it mean. There was a paper in '94 published that says a system is said to be real-time if the total correctness of an operation depends not only upon its logical correctness, but also upon the time in which it is performed. So the key notion here is that we're generating some output for a given input, but not only does that have to be logically correct, we also have to complete that operation in a specific time. So we have a deadline. And if we look over to Wikipedia, we can see that real-time systems, as well as their deadlines, are classified by the consequence of missing a deadline. And we can roughly split this up into three categories. We have hard, where missing a deadline is a total system failure, and we'll see some examples of that on the next slide. We have firm, where infrequent deadline misses are tolerable, but may degrade the system's quality of service. The usefulness of a result is zero after its deadline. And sometimes we have this in audio. You can imagine playing a file back from your computer, where you might drop the occasional packet, and that might sort of be acceptable in that situation, but you can't use that data once you process it if you've missed your deadline. There's no way to kind of send it out the speaker in the next block and move it towards your ear, because if the speaker hasn't moved, it hasn't moved. And then we have soft, which is where the usefulness of a result degrades after its deadline, thereby degrading the system's quality of service. So in the soft area, we have things like production lines, where slowing things down might cause other bits of the system to slow down. Hard real-time, we have things like anti-lock brakes, car engine control systems, and monitoring systems, particularly medical equipment. And in the middle, we have this firm area, which high-frequency or low-latency trading sometimes dips into here. Audio, video game visuals, where missing the occasional frame might be acceptable. So what's the difference between standard and real-time programming? And it essentially boils down to real-time threads. So a real-time thread can give you an uninterrupted period of time to run. However, if you exceed this deadline, then you may be put to sleep, and that can mean you can miss your deadline. And also, the next time you get run, you may be declassified as a real-time thread, and then you don't get these real-time privileges anymore. So the key thing is to not miss your deadlines. And I'll reiterate that because it's very important. Don't miss your deadlines, otherwise it's difficult to make up for. So in non-real-time, we have a whole bunch of tools available to us, but real-time, this is kind of very much reduced. We have to do some CPU work. We're generating output for given inputs. We might have to do a context switch, especially if we're on a general operating system, but we need to kind of minimize the costs of those. And if you can, on embedded systems, have a dedicated core to really kind of reduce this. That's a good situation. Memory access, we want to really only be dealing with memory that's heavily cached, and particularly avoid memory being paged. And this can happen if you load a lot of data, such as big audio files, but then don't use it in a while, and other processes contend for that RAM, then you can end up getting that page to disk, and then reading from that block next time you're run can be a costly operation. So there's various techniques to avoid that, such as using mlock, virtual lock on Windows, or having other threads kind of constantly read the memory to indicate to the OS to keep it in memory. System calls we need to avoid because those are blocking operations. They're synchronizing with the OS, so they're essentially unbounded calls. Allocations and deallocations are similar. They take global locks on the heap, so you're contending with other parts of the system, and exceptions because they require memory allocation. The other thing we need to avoid is priority inversion. And this is where you have a real-time or a high-priority thread interacting with a shared resource with a low-priority thread. You can get into this situation in surprising ways. So if we take this example where you might think that storing to a shared pointer using atomic store is real-time safe, but if you have a low-priority thread that's trying to do a store or a load at the same time, it might gain this mutex. And if that thread happens to get descheduled after it's obtained the lock, then the real-time thread will then be waiting for that operation to finish so you can miss your deadlines. And this isn't acceptable. Also, we probably don't want to make copies, so this is a kind of very trivial case where you might be calling update data, passing in a vector. If data isn't the correct size, then this can cause a resize and hence an allocation. That's fairly obvious, but this can sneak into some hidden places as well. So you might assume that moves are real-time safe, but if you're dealing with legacy code, you might not always be getting a move. So here we have some kind of legacy object. It has no R-value semantics, so it only has a standard copy constructor and assignment operator, and then maybe we construct a parent object that has a vector and one of these legacy objects, and in our program we try and do a move from B to A, but we're going to end up calling this copy constructor or assignment operator here because we don't have R-value semantics, so this can incur the kind of hidden costs that we looked at before.
So some vocabulary that we will need throughout this talk, we'll be using the terms blocking and wait free. So blocking is particularly bad on a real-time thread because it will incur usually a context switch or a lock or some system call or puts the thread to sleep. And that's very, very bad because your CAS are likely to be invalidated because another thread will have run or another process will have even been run. And if your memory is contended, your memory might even be swapped out. So you really want to avoid any blocking operations. Then slightly better are non-wait-free operations. That means the execution time is somehow unbounded, usually through a loop where the looping condition is something you don't have control over. We'll see some examples of that later. And then the best thing is wait-free. That means that there are no unbounded loops and you can reason about the execution time, the maximum execution time of your function.
So in summary, we can essentially say one rule here, which is don't block. And then we can split that into two. We can say no system calls and no waiting to acquire a lock of any kind. And we'll see why in a sec. So how do we go about winning in real time? We're going to present this flowchart today, which essentially poses a series of scenarios and questions you can ask yourself about your system to try and make life easy for yourself. So what we want to do is kind of stay up in the clouds where life is nice and easy and avoid going too far down into real-time fiery hell. So
the design patterns, the real-time design patterns, which we will show you in this talk, they've been all collected into a library called the Farbot library, which is online on GitHub. And it's really, over the years I've been programming, and me and Dave, we've been encountering the same types of real-time design patterns that we've used over and over again. And I started collecting them and putting them into one library. And now, just as a side note, we're not going to talk about memory order here today because we don't have enough time, but the library does make use of memory order, if you know what that means. Because I've put all of this code into one place and redesigned it and refactored it and made it all unified, that they all use the same names and the patterns, I rewrote a lot of the code, so I would say it's early alpha development because I haven't tested this rewrite very well. So there might be bugs, and please contribute your real-time patterns to the library.
Okay, so if we dive into the flowchart, the first question we need to ask ourselves is, are we sharing data between threads, or are we simply passing that off? If we're passing, the solution is to use FIFOs, but they're kind of built from some of the concepts that we're going to discuss in a minute, so we'll cycle back around to that towards the end. So if the answer to this question is that we're sharing data, then we need to go on to the next section. And the first thing really before you start thinking about real-time is, are you actually interacting with a real-time thread? And if you're not, then probably just use locks. You could reach for std mutex in this situation. It's probably the simplest way to work in a non-real-time context. So just think about that before you start going into some real heavy lock-free concepts. But if the answer is that you are interacting with a real-time thread, then we need to ask another question. And that is, are you sharing suitably small data? We've left that a little bit ambiguous, but we'll tidy that definition up in a sec. So here's a classic example where we have some real-time thread indicated by the red bar on the left and a non-real-time thread indicated by the green. And we're processing some data, and then a non-real-time thread is kind of modifying this shared variable called gain. Now, is this okay? And also think about on a single core machine where we won't have concurrent access to gain. It's not okay because sharing data between threads where one of them is a write is a data race. And a data race is undefined behavior. So it's not okay. And the reason for this is the optimizer can mess with your code. So what it can do is assume that you haven't written a data race, so whilst this loop is running, gain isn't going to change. So it can actually hoist it out into a register, which kind of looks like this conceptually. And you might think, oh, that's not too bad, gain isn't going to get updated mid-block, but it can be worse than that. So imagine the scenario is actually like this, where you have some real-time thread entry and then just continuously spinning while some flag is true. We get some data, we process that data, but what if process sensor data happens to get inlined? Now, if the same optimization and the same reasoning is applied from before, then this gain can get pulled out into a register at the start of your real-time thread entry, so that's going to be cached, and then this effectively has no effect. So because we've written a data race, we have undefined behavior, and literally anything can happen to your program at this point. So back to the flowchart. We lost sound. So the question we need to ask is, are we sharing suitably small data? And if the answer is yes, then the solution is to use an atomic. So here we've swapped our gain for a stood atomic float, and now we can load and store. And using the atomic means that loads and stores are synchronized between them, and it also stops the optimizer from doing those things that we saw before. However, we need to check if doing this atomic operation is lock-free in hardware. And the reason for that is if you have big objects, then you might be able to store them in atomic if they're trivially copyable, but it will insert locks. So we need to check this statically is always lock-free before we go down this route. So atomics ensure tear-free and synchronized manipulation of shared data, but we can only do a subset of operations on them. We can only store, load, do atomic addition, subtraction, exchange, and compare exchange, which we'll see more of later. If you want to look into more atomics, Herb Sutter's Atomic Weapons talk is a really good resource for that. So if we summarize in this scenario, we have multiple threads that are needing to mutate some shared data, but we have a trade-off that the data needs to be small, it needs to fit lock-free into an atomic, and only certain operations are allowed. We can't do multiplications on atomics, for example. And some examples of this are where we're sharing gain values, level meters, automation values, parameters, those kinds of things. So small blocks of data. So if we tidy up our definition, we can say, are we sharing is always lock-free data? Yes, use atomics, but if no, we need to go on to the next section. So the next question is failure to acquire the shared resource okay? And think about this carefully, because if you can deal with a failure, then the answer might actually be to use a lock. So in this scenario, we have some shared resource that's quite big, like a wavetable, could be several hundred floats, something like that, and we're going to guard access to it with this mutex object. On our non-real-time thread, we're simply going to take a lock to guard access to this, and then once we've created a new wavetable, perhaps a user's loaded a new file, we can just swap those. On our real-time thread, we can do an operation called a try lock. So we use a stood unique lock here with this stood try to lock argument, and only if that operation succeeds, then do we do something with wavetable. The key here is that if we don't get that lock, we need to be able to fail, and fail gracefully. And in audio, that might be something like storing the last few samples and then fading out to avoid a glitch in the output. What this really means in this situation is we'll only fail to acquire this lock if a new wavetable is currently being loaded. So we know we're going to lose access to that resource in the future, so we're just kind of bringing that deadline forwards, and then we'll probably get a new resource soon. But we need to ask, what is this mutex object? And what happens here when the unique lock goes out of scope? So if we look at stood mutex, we can see that try lock is wait-free, which is great, so that's a non-blocking operation. But according to the documentation, it can fail spuriously. This probably isn't okay if you're streaming something from disk and you might have the occasional dropped packet. And that can happen for similar reasons, that condition variable can fail spuriously or wake up. And also, the real thing that we want to avoid here is that std mutex unlock can block, and that's if another thread is waiting on the mutex, there'll be a system call involved to notify that thread. So we can use a different kind of lock, which is a spin lock. If we replace all the uses of mutex there with spin lock, this is now a good pattern to follow. So if we take a quick look at our really basic spin lock, it essentially is just an atomic flag, so we know it's going to be operated in hardware. Our real-time operations are unlock, which is just going to clear the flag, and try lock, which is going to just once try and set the flag, and if it succeeds, then we've gained the lock. On the non-real-time thread, we're going to call this lock operation, which is just going to continuously spin and try and get this lock, and that's going to block until it succeeds. So the key thing here is that there's no sleeps, no yields, no interacting with the operating system. There are improvements you can make to this, like memory ordering and pause operations while spinning, but no system calls. So in this scenario, we've got big data, can't fit into std atomic lock free, but we have the caveat that failure to acquire the resource is okay. The trade-off is that the non-real-time thread is going to wait on the real-time thread. And this can be problematic if your real-time thread is almost constantly running. It might be that your non-real-time thread kind of fails to jump in at an appropriate point. And also the real-time thread will have to fail gracefully. And examples of this are where you're passing audio samples, wavetables, filter coefficients, those kind of things. So if we go back to our flowchart, if failure to acquire the shared resource is not okay, then we need to go to the next stage down. So the question here is, does the real-time thread mutate the object? And if the answer is no, then we can do this CAS loop operation. So here's another classic example from audio, where we have a real-time thread using some filter coefficients and a non-real-time thread that wants to update those filter coefficients. So we can see here the use of those coefficients, but bytecode coefficient is quite large, it's 5 floats. So naively, we might think, right, we'll just stick that in a std atomic and then load that out and use that safely in the real-time thread. But the problem is our static assert that we said we should always use is going to fail here. So this isn't now a lock-free operation. So if we simplify the code a bit, we put all that processing into this process bytecode method, we can approach the problem slightly differently. So what if we were to store a pointer to the bytecode coefficients rather than the actual object? So this is going to work. Now we can just create a new pointer and store it in the atomic, but there's going to be a huge memory leak because we've essentially no way of knowing when that's safe to delete. So that's not real-time safe. What we want to do is have some kind of flag that's going to indicate whether the resource is being used by the real-time thread. So if we create this atomic is in audio thread flag, then we can set this to true at the start of our real-time thread, safely use the coefficients, do our processing, and then set it to false when we're done. In our non-real-time thread, we're now going to create our new coefficients, and then continuously check this flag, and only when it's not in use by the audio thread, then we can continue to swap them, and obviously delete the old one. Now, this kind of looks okay, but there's a real problem here, which is where the audio thread, the real-time thread, can change this flag in between the time when we've checked it and when we're assuming its value. So this is called the ABA problem, and this is what we want to avoid. So the approach here is that somehow we want to combine that flag that's notifying whether we're using the resource and the resource into one. So with this CAS Exchange Loop approach, we can store the bytecode coefficients in a unique pointer, so we have proper memory usage, and then we just store a pointer to the resource that we're supposed to be using. Now, in our real-time thread, we can exchange that pointer with this null pointer value, which is going to be our flag to indicate that it's in use by the real-time thread. So we do this atomic exchange, now we can use coefficients, and when we're done, we need to put that coefficients back into the atomic, which is going to signal to the non-real-time thread that it's safe to modify. In our non-real-time thread, we're going to do this compare and set exchange loop. So we create our new coefficients, then we get the value that we expect to be in the stood atomic bytecode coefficients, and then we try and do this compare exchange strong operation. So that's going to set the value of bytecode coefficients to the new bytecode coefficients, but only when expected is equal to what is stored in our storage member. If that fails, then it means that the real-time thread is in use because it has the value null pointer. Expected here is going to get modified to the current value of the bytecode coefficients, so we need to update that at the end of our loop. Now, once that operation succeeds, we can simply move the new bytecode into our storage, which is going to delete the old one, and we haven't leaked anything. So that works, and everything is good. There's a slight caveat here, which is that changes on the real-time thread are going to be lost. This is a one-way operation. There's no way to get data back from the real-time thread to the non-real-time thread. So that's something to be aware of. In Farbot, we have this non-RealtimeMutatable object, which nicely encapsulates all this logic and operations. So it's a templated class. We simply say we want a non-realtime mutatable set of bytecode coefficients. Then on our real-time thread, we can call a real-time acquire, which is going to do a non-blocking acquire, give us a reference to the coefficients. We can use those, and when we're done with them, we can do a real-time release, which is going to release that operation. In our non-real-time thread, we do a non-real-time acquire and then a non-real-time release. And that essentially encapsulates all that null pointer business that's quite tricky to get right in code. Of course, we want to do this in an RAII way, so we have this scoped access class here that we can simply use to avoid doing the acquire release ourselves, and then we have this templated Boolean to say whether we're on the real-time thread or the non-real-time thread. So in summary here, we have the scenario that we're using big data, so we can't just use an atomic. The non-real-time thread can mutate the object, and the real-time thread can't be in a situation where it fails to acquire the resource. And our trade-off that we have to think about always in real-time programming is that the real-time thread cannot mutate the object here, and the non-real-time thread is still going to do this waiting on the real-time thread, so that might be a consideration. Also, sometimes there's overhead of copying from the non-real-time thread as you store data into the non-real-time object, or non-real-time mutatable object. And again, similar to before, this is for sharing things like audio samples, wavetables, and audio large-ish data. So if we go back to our flowchart, we can ask the question, does the real-time thread mutate the object? No, use that CAS loop. However, if the answer is yes, we need to move on to our next question.
Okay, so now we have the other way around. So now the real-time thread wants to mutate the object, but the non-real-time thread, the message thread, is not mutating the object. So we're going down this path now. And there's a technique that you can use, which is called double buffering. Essentially, there's like 2 slots for your data, and there's a real-time slot for the data and a non-real-time slot. The real-time thread only always uses the real-time slot, and the non-real-time thread only always uses the slot on the right there. And let's just say at the beginning, they're initialized with data A and B. Now, the real-time thread, when it's producing data, it can simply override its real-time slot with data here. And whenever the non-real-time thread is ready to read that data, it swaps the slots atomically, and now the D is in the other slot, and now it can read that D. And even if it takes a long time to read that D, more data can come in on the real-time slot without interfering with the non-real-time slot. So in code, it kind of looks like this. You have this index variable, which denotes which slot is currently used by the real-time thread. The real-time thread always writes to its own slot, and the non-real-time thread, just before it reads, it swaps the slot index, so it swaps the slots, and then can safely read from its own slot. Now, there's a bit of a mistake here, that if this update spectrum UI button clicked is called 2 times in a row, you will get an error. You'll get a mistake, and to show this, let's go back to this image here. So again, we have our 2 slots. We are writing new data into the real-time slot. The newest data now is C, right? So I want to read that data, so I swap the slots, I read C, but now before the real-time thread has a chance to run, I read again. And then the problem is you swap again, and now you're reading something that's old. So you're reading B now, which is an old value. So to fix that, what you need to do is you need to introduce a new flag to tell the non-real-time thread that new data is available and that it should swap. Now, as Dave showed before in his part, naively what you would do is you would create a new flag called new data and put it into a new separate atomic variable. That usually doesn't get you very far. You will run into these ABA problems. So what you really need to do is put that flag into the same atomic variable as the index and always update them atomically. And this is exactly what we're doing here. We're creating a new bit called bit new data, and that's set when new data is available. And on the non-real-time thread, we check that bit, and only if that bit is set do we then atomically swap the index and clear that bit. That's very important. If you don't do that atomically, you'll run into all of these ABA problems. Now, this is nice. It's almost correct, because by doing this, we actually ran into another problem. We've actually introduced a new error here, and that's before the the real-time thread would only ever read the index. But here, we're actually reading the index and then storing the index. And because we're doing that in two separate instructions here, the non-real-time thread could jump in between, and then we would have a problem again. So we need to introduce yet another bit called the busy bit, and the busy bit is atomically set when we read the index and then atomically cleared when we store the index again. And now the non-real-time thread can have a CAS loop on this busy bit, can wait until the busy bit is not set, and when it's not set, only then will it swap the indexes. Okay, so this is quite complicated. It works, but having to write this over and over again, this is one of the design patterns that I put into Farbot. There, it's called now RealtimeMutatable because only the real-time thread can mutate the object, and it's just as the other non-real-time mutable object as before. It works exactly the same. There's a scoped access. It's really easy to use. So in summary, if your data is big, it's bigger than that you can atomically change lock-free, and only the real-time thread is mutating the object and the non-real-time thread is only reading, then you can use this. The trade-offs is that the non-real-time thread is not wait-free, right? But that's okay. It's a non-real-time thread. The real-time thread is still always wait-free. And unfortunately, this pattern has an overhead of copying on both the non-real-time and real-time thread. So if copying takes a very, very long time for you, then maybe this is not the pattern for you. Examples are any example where the real-time thread creates some kind of data which it wants to share to other threads. This could be some visualizations, frequency spectra, oscilloscopes, etc., etc. Okay, so let's go to the last case now. The last case is both threads, multiple threads want to mutate the data. But before we go down to that last item, we're going to jump all the way to the top again because we left something out at the beginning of the talk, is where we said, are you sharing or passing objects between threads? And if you're passing, well, then use a FIFO. So the humble FIFO, who hasn't used a FIFO in real-time code before? It's very, very, very important data structure for real-time code. And the reason is, with all of these design patterns I showed you, the atomic, the non-real-time mutable, the real-time mutable, when you're creating data, you're always overriding the oldest. And that's a problem if the other threads don't pick up that data. For some data, that could be a problem. Like if you have a deallocation queue, a garbage collector, if you're just going to overwrite the old data you're putting in there, then you can have a big, big memory leak. So the FIFO is really good when it's really important that things don't get lost, when you really want to pass ownership of an object from one thread to the other. And it does this by buffering the objects in a buffer. So that the other threads have some time to pick up that object. Now, in real-time code, a particular variant of the FIFO is used. It's called a ring buffer. I'm sure you've all seen it. And it's used because it has a fixed capacity, so you don't need to do any allocations while using it, which would be forbidden on a real-time thread. Now, within this ring buffer, though, there are even more variations. And so when you are using a ring buffer or using a FIFO, you should really ask yourselves two questions to get this right. First of all, will more than one thread concurrently read or write into that FIFO? And the second question is, think about what will happen if the FIFO is full when writing or empty when reading. So let's say on the producer side, we're producing data, we're putting stuff into the FIFO. First of all, is it going to be one thread that produces data or multiple threads? And if it's full, should it report that it's full, let's say by some kind of Boolean flag that it returns, like it returns false when it's full? Or should it just overwrite the oldest data silently when it's full? On the consumer side, you have the same thing, single thread or multiple thread. And should it report if the FIFO is empty, or an alternative, it could just always return a default constructed element when it's empty. Like if it's a pointer, it would just always return null putter, or if it's an int, it would just always return 0. So that means you have 16 variations of a FIFO, quite a lot. And just to give you some examples to help you understand this, if you, in audio, for example, have an audio thread, it's a single audio thread, and it's downsampling some audio to display on a single UI thread, then, well, what would happen if that UI thread would hang? You know, you have the spinning beach ball of death on your Mac, so it's hanging for 5 seconds, all of a sudden it wakes up again. Well, you don't really want to show the data from 5 seconds ago. That would be useless, right? That data is already gone. So in this case, it's actually quite good if the producer overwrites when it's full, right? You should just overwrite the old data when it's full. And in this case, well, if the FIFO is empty, then something really bad has happened, because then your audio thread is not running properly. So you should probably report that and show some kind of error. Another example would be you have multiple sensors. They all come from multiple real-time threads. And you have a single checker thread which just checks if any of the sensor data have reached a certain threshold. Now, in this case, it would be really, really bad if any data is lost, right? Because you might be losing that bit of data that went over the threshold. So here, you really want to report if the FIFO is full. But on the other hand, if the FIFO is empty and you're just reading zeros, well, a 0 won't hit the threshold. So you might want to use this variation of the FIFO. And I'm asking you all these questions not because it's fun, but because all of these FIFOs come with different costs. So you can choose which FIFO variant you want to use, and with this diary you can see if it's weight-free on a read, weight-free on a write, or weight-free on both a read and write. And the last example I just showed you with the sensors, for example, that would only be weight-free on a read. I also want to point out this one, this gray one, which is sort of the most general FIFO because it's a multiple producer, multiple consumer FIFO. It reports when it's empty and it reports when it's full. So with that, you could basically emulate any other of these FIFOs. But it's also the one that incurs the most cost because it's neither weight-free on the write or the read. In Farbot, there is a FIFO. I'm not going to show it to you how I wrote it. It's probably one of the hardest things I ever wrote, and I took inspiration from the link down there from Alexander Kristanovsky. It's the most general variant, the gray dot I showed you, is 60% slower than Boost FIFO, so it's not the fastest one. It's definitely faster than the naive solution, so you can write a very naive ring buffer with a spin lock. That's very easy to do. But for example, Boost only has this very general case as a FIFO. It doesn't have all those other 16 variants. And if you use any of those other variants, then my FIFO is comparable with Boost FIFO. Still, why would you ever want to use Farbot's FIFO if Boost's FIFO is always the same speed or better? It's because Boost's FIFO, unfortunately, throws a lot of false positives with the thread sanitizer. And if you're debugging your real-time code with thread sanitizer, then maybe it's good to use the Farbot's FIFO first because it won't have any false positive. It won't throw any thread sanitizer messages. And then you can check all your other code. And then if you really want to have the fastest and greatest, then you could maybe switch to the Boost FIFO. One of the things that you can do with a FIFO, and which is commonly done, is you implement a very powerful function called call async. Now, call async takes some kind of non-real-time safe function that you want to do, like logging in this case, and defers it to a non-real-time thread. The call async itself is real-time safe. So you can call async on your real-time thread, and then the non-real-time part, the non-real-time lambda that you will do, will then at some time later be executed on a non-real-time thread. It's very, very simple to implement with a FIFO. So here, in this case, we have a real-time thread. It wants to do some logging, so it calls call async. Call async will now take that lambda and move it into the FIFO. And now it's very important that this FIFO, and you can only check this yourself, that this lambda is a real-time movable. So the things that you capture in your lambda all have to be real-time movable. Otherwise, it will not be real-time safe. Then on the non-real-time thread, you can call this process function, which just simply pops all those lambdas from the FIFO and processes them. Now notice here, and this is very, very annoying, waking up a thread is not real-time safe. It might call a system call. So you cannot wake up the thread at this call async. So what you need to do as a workaround, there are other workarounds, but the simplest workaround is that your non-real-time thread on a timer just keeps checking if there's anything in the FIFO, and if yes, it will execute them. Okay, so summary of the FIFO. Again, your data is too big to be used with atomics. You're transferring objects from one thread to the other. The trade-offs are that the capacity of the FIFO, you have to set that to some value. It can't grow on a real-time thread. You have to think about the behavior of what happens when the FIFO is full, and there is obviously a potential overhead of copying stuff in and out of the FIFO. Okay, so now we can go all the way back down to the graph, because now we get to have the FIFO. We can talk about the last item. We're no longer passing data from one thread to the other. We're just sharing data. We have like one global data, and multiple threads want to mutate that data and read the data. So we both think there's no real safe way to do that directly. So I think it's impossible to have multiple threads write to some data and that all be lock-free. So our suggestion for a workaround is you choose a single thread which is in charge of mutating. It could be the real-time thread, and then all the other threads simply pass messages to that thread and tell it to mutate that data. So it's a kind of a workaround. Just as an example how that could work, I've recently been writing some of this code. I have an audio thread which is mixing a lot of audio sources, and the user in the UI can add audio sources to the source list, but also there are some real-time events coming in on a real-time event port, and those events could add sources as well. So how would you do this? Well, you have this source list, and it's a real-time mutatable object, because in this case I wanted the real-time thread to be in charge of the mutations. And then we have this AsyncCaller, so that anything that comes on if a non-real-time thread wants to change the source list, it will have to use this AsyncCaller to defer the call to the real-time thread. So just to show you this add source function, the real-time thread will take this branch. It will simply use the real-time mutatable. It will then be able to change that object. If a non-real-time thread comes in and wants to change the object, it will have to do the call async. It will have to defer the processing to the real-time thread to change that source list. The real-time audio callback function here, this mix all sources, that gets called repeatedly every time there's new audio there. It will first process those real-time events which may add or remove sources. Then it will process all those lambdas that came in from the non-real-time threads, which may also add or remove sources, and then it can simply use those sources. And just to stress here, this is only about mutating objects. So a non-real-time thread can still safely read from the source list at any time, as shown down here, where we just print all the sources that are in the source list. So the summary for this, again, your data is big. You're sharing between real-time and non-real-time threads. All the threads may mutate the object. Then we would suggest to use this design pattern. The trade-off is there has to be one thread in charge of changing the data. And it's quite complex, right? And so there's nothing in Farbot that could really abstract this away, because it really depends on your use case of exactly how you want to implement this, what exactly your messages are to mutate the object that you're mutating. Okay, so that's our graph. In summary, you're sharing any kind of data between threads. What do? Well, first you ask yourself the question, am I sharing or passing data? If I'm passing data, use a FIFO. And then if you're only dealing with non-real-time threads, please just use locks, right? Don't go any further down. Don't try any of this fancy stuff. You'll just get it wrong. If you are using real-time threads, is the data small enough? Use atomics. Then maybe it's okay if you don't acquire the resource. Use a try-lock. What if only the non-real-time thread changes the data? Use a CAS loop, or use the Farbot non-realtime mutable object. Or if only the real-time thread mutates the data, use the real-time mutatable object, and if they both do, then use this slightly complicated combination of a FIFO and the real-time mutatable or non-real-time mutatable object. Okay, so with that, I hope you can all relax. That diagram will help you to escape hell. Well, will it? I'm not quite sure. I've used it a lot, and I still get bugs all the time, so Welcome to our last section, how do you debug real-time code? First of all, I can't stress this enough, use Thread Sanitizer. It really helped me so often in code. It brings up things where you would never think it's a data race, and it's very, very powerful. I have to say, and I'm not sure, this is maybe my Ubuntu version I'm using, the GCC Thread Sanitizer didn't find all the data races, where the Clang Thread Sanitizer definitely seems to be finding a lot of them. I saw some Stack Overflow issues on this. And also make sure to test the production code. And I can't stress this enough as well. The problem with Thread Sanitizer and data races is that the C++ standard says that I/O operations synchronize between threads. And it doesn't really specify what I/O operations are. And maybe some people in this room know, I suspect it to be system calls, right, actually. So that any system call will actually synchronize between threads. That means there will not be a data race anymore when you do some kind of system call. That means if you're doing some kind of logging in your code, that's a synchronization event, right? So that means all of a sudden these data races don't show up. Even worse is if you're doing sleeps. So sometimes a sleep, if it's a short sleep, will not call a system call. It will just do some pause instructions. But if it's a longer sleep, it might decide, hey, there's a longer sleep. I'm going to do a system call to put this thread to sleep. So even if you're just changing timings in your app to help you with the debugging, it might actually remove some of the data races that are in your code. So it's very, very tricky to debug data races. Really try to debug your production code as much as possible. Then use strace to try to catch system calls on particular threads. strace is very handy. It will show you exactly which threads called which system calls. You can then just grep on a particular thread ID and see if your real-time thread ever called a system call. And to catch allocations, no, allocations don't always call a system call. Locking, if a lock is not contended, it won't call a system call. And they're very rarely contended, but they could be contended. So to catch those, use LD preload, where you override some of the functions in a little dummy library to log whenever one of these functions are used. But is there anything we can do statically? I mean, this is all runtime. So I just want to show you an example again of the FIFO and Farbot. There's a really, really rough version of this. There, as I said before, we're pushing into the ring, or we're moving into the ring buffer on the FIFO, right? And this push operation is really only real-time safe if that move is real-time safe. So what I would really love to write everywhere in my code is like a static assert, is this thing real-time move assignable? That would be great, because if I put that into my FIFO, I can guarantee that anybody using my FIFO will have a real-time FIFO. Now, Farbot does have it's a real-time move assignable. It's simple template hackery. It just checks if it's trivial, if it's a trivial type, it's trivially movable and trivially copyable. And then it has some specializations for some container types like vector set, unordered set, some of those unique putter. So it checks that, but it can't check all the types. So if you want to use this, you're going to have to specialize for your own types. And Dave and I were really thinking if there's any way to do this in a better way, to actually, like if you have a struct, can it check all the members of the struct that these are all real-time movable? And if yes, is the whole struct real-time movable? And unfortunately, something like that is currently not possible in C++. Maybe with reflection, I'm not sure. But currently, it's not possible, and it would be great to have language support for something like is real-time movable or real-time assignable, etc. Okay.
So in summary, the real thing that we need to be aware of is our deadlines, and don't miss them, because then you can't really recover from them. And beware of hidden costs. We've just seen a lot of examples where potential moves can kind of incur costs that perhaps aren't obvious on the surface. The best advice we can give really is to follow the flowchart. If you kind of follow that reasoning, you should end up with the simplest example possible, which gives you the greatest chance of success, really. And also, as Fabian just said, use instrumentation to check your code. This is complicated stuff. It's difficult to reason about, and instrumentation is really going to save you here. So that's all we've got for today. I've been Dave Rowland.
I'm Fabian.
And yeah, I think we've got some time for questions. question here. I think there's a mic. You can use that.
Hello. Thank you for the very good presentation. I would like to know about the Intel processors has transactional memory mode. And what about transactional memory usage for real-time processing?
Good question. I haven't been following the transactional memory proposals too closely. Did you look into them?
No, I don't know. I mean, I know there's like emulations in software, but if you have real hardware support, I haven't looked into that, if that's real-time safe. And if the library could use that. But that's a good point. I'll definitely check that out.
Yeah.
Okay, thank you.
Is there a question at the back?
I wanted to ask if the real Fixbot library is used in any production software, and if you can share which software specifically.
No. So definitely the design patterns I have an internal library which I like kept copy and pasting, and then I did tweaks to it for the different use cases. And I'm fairly sure. I mean, they're all unit tested, so I'm fairly sure like that the design pattern is correct. The problem is for this talk, I put everything together, cleaned it all up, used some of it was C++ 14 code. I cleaned it up to be C++ 17, changed a lot of the names, added that scoped axis thing, and I did that all real quick. If I wouldn't want anybody to rely on this for production code right now. I think it needs more testing, but that's why I put it up on GitHub, and I'd love some other people to share their design patterns as well.
You just said something very interesting, unit testing. How do you unit test multi-threaded code?
Yeah. I mean, it's not very good unit testing. I mean, I do unit testing like I expect, like, for example, for the FIFO, right? I let hundreds of threads bombard this thing, and then I have a little, I always push unique values, and then I check that I actually always pop all of these values and that they came in the right order. So I spin up, for the FIFO, I spin up multiple reader threads, multiple writer threads, and then I can check sort of if if nothing was lost or nothing was duplicated, and if things came in the right order. But of course, is it thread safe? Because there might be a very, very rare condition. I mean, I think it is data race safe because the thread sanitizer is actually very good on Clang. I'm confident about that. And on the FIFO, it's also, I read it in this paper I showed that was at the bottom of the screen, so it is a published algorithm I'm using. But that doesn't mean I didn't write a bug, right? I mean, it's very hard to test for that.
Okay, I think that's all the questions. All right, thanks for coming, everyone.